It is the spark that drives every beat. A violent reaction, fueling life itself. This is the power of potassium.
I want you to picture something for a second. Imagine you're holding a piece of metal in the palm of your hand.
Okay.
But, this isn't like a steel coin or a piece of copper wire. This metal is so volatile, so incredibly unstable, that just the invisible moisture in the air around you is enough to cause it to violently break down.
Yeah, it's highly reactive.
Right, like if you drop it in a glass of water, it literally explodes. It's a severe chemical hazard. But right now, as you are listening to this, that exact same explosive element is quietly coursing through your veins, commanding your heart to beat.
It sounds like a complete contradiction, doesn't it?
It really does.
Like a biological impossibility.
Yeah.
But we're talking about a very real, very tangible building block of our universe. Today's deep dive is into a stack of articles, research papers, and chemical profiles covering element 19 on the periodic table, which is potassium.
Right.
Its chemical symbol is K, which actually comes from its original Latin name, Kalium.
Oh, I always wondered about the K.
Yeah, it's Kalium. And our mission today is to really solve this chemical mystery. How does nature take a metal that wants to aggressively react with almost everything on Earth and use it as the fundamental bridge between deadly explosions and essential biology?
Okay, let's unpack this, because looking at the physical properties of pure potassium in the sources, it breaks every single rule of what I thought a metal was supposed to be.
Oh, for sure.
I mean, it doesn't behave like iron or aluminum at all.
No, it really doesn't. Potassium belongs to the alkali metal family on the periodic table.
Okay.
And they are infamous for their extreme chemical reactivity.
Right.
I mean, to understand the biology later on, we first have to understand the sheer chaos of this element in its raw form.
We'll have to talk about what it actually looks and feels like, because it is bizarre. It's incredibly soft.
Yeah.
If you had a chunk of pure potassium on a cutting board, you could just slice right through it with a standard kitchen knife.
Just right through.
Right. It's a metal, but it behaves physically like, I don't know, a deadly stick of butter.
A deadly stick of butter is actually a great way to visualize it.
Okay.
When you slice it open, for a brief fraction of a second, you see this beautiful, bright, silvery metallic shine on the inside.
But only for a second.
Literally within seconds, that silver shine disappears. It tarnishes almost immediately just from making contact with the ambient oxygen in the room.
Wow.
And its physical weirdness goes further. It is one of the lightest metals known to science. Its density is actually lower than water.
Which means it floats.
Exactly.
So we have a floating butter-soft metal, but you really, really do not want to put it on water to test that buoyancy, because, the chemical reaction that happens when potassium touches water is incredibly cinematic.
It is. It's one of the most visually stunning demonstrations in chemistry.
Mm-hmm.
But we need to look at why it's so violent.
Right.
It all comes down to its atomic structure.
Yeah.
So potassium is element 19, meaning it has 19 electrons.
Okay.
18 of those electrons are perfectly organized in stable inner shells. But that 19th electron is stuck all by itself in the outermost shell.
So it's like the odd one out.
Right. And potassium is absolutely desperate to get rid of that single valence electron to achieve atomic stability.
It just wants to dump it.
Exactly. So when pure potassium touches water, it sees an opportunity. It violently forces that extra electron onto the water molecules, physically ripping the water apart into hydrogen gas and hydroxide.
So the explosion isn't just the metal itself catching fire. It's the metal tearing water to shreds, creating hydrogen gas. And wait, where does the spark come from?
The heat of the molecular breakup.
Oh, wow.
Yeah, ripping those molecules apart releases a massive amount of thermal energy. So in one instant, the potassium generates highly flammable hydrogen gas and the heat to ignite it.
That is wild.
It is. This causes a violent popping explosion, and it produces this signature brilliant purple or lilac flame.
A purple flame, which means, you can't just leave a deadly stick of butter on a laboratory shelf.
Definitely not.
Like, if it wants to explode when it touches water and it tarnishes instantly in the air, how do scientists even store this stuff without blowing up the building?
Well, you have to create an environment where it cannot access its trigger. Pure potassium must be permanently stored, completely submerged in mineral oil.
Oh, oil. Okay.
Yeah, the oil creates a thick liquid barrier that contains no oxygen and no moisture, effectively placing the metal in chemical timeout.
Okay, but this brings up a massive logical hurdle for me.
What's that?
If this metal is so unstable that it is constantly trying to react with everything, like to the point of tearing water apart just to lose an electron, it means it doesn't just exist sitting around in nature in its pure silvery form. It's always hidden away, already reacted, locked up in compounds with other elements. So how did humanity ever figure out it existed in the first place? I mean, you can't just mine it, right?
No, you can't. And it took until the early 19th century to crack that code. Specifically, 1807, thanks to an English chemist named Sir Humphry Davy.
Okay.
What's fascinating here is that Davy didn't discover potassium by mixing chemicals in a beaker. He used what was at the time a cutting-edge technological tool, which was electricity.
Oh, he used a massive battery, like the concept of electrolysis.
Yes, exactly. Passing an electric current through a substance to drive a chemical reaction.
Right.
Davy took a compound called potassium hydroxide, which is commonly known as potash, which, by the way, is where the name potassium comes from.
Oh, I see.
Yeah. He heated this solid salt up until it melted into a molten liquid. Then he took his battery and ran an electric current straight through it.
So if potassium in a compound has already given away its electron to become stable, Davy's electricity is basically acting like a molecular crowbar?
That is a perfect way to look at it. The electric current was literally forcing electrons back into the potassium ions, completely reversing the natural reaction.
And as he ran the current, he started seeing these tiny, shiny metallic droplets forming in the molten liquid. I mean, that must have been terrifying, actually.
Oh, absolutely.
Because he's creating pure, highly reactive potassium right there on the table.
It was a monumental breakthrough.
Yeah.
Potassium was the very first metal ever isolated using electrolysis. Davy proved that electricity could be used to separate elements from compounds, overpowering their natural chemical bonds.
Yeah.
It opened up an entirely new chapter in the history of chemistry.
It's incredible, but here's where it gets really interesting and where we have to connect Davy's laboratory to our own bodies.
Right.
Because the human body is roughly 60% water.
Yeah.
So if I consume potassium, why am I not swallowing tiny explosives every time I eat a meal? Why isn't there a purple flame bursting in my stomach?
It's the most intuitive question to ask, and the difference comes down to that single electron we talked about earlier. There is a profound biological difference between a pure metal and a dissolved ion.
Let me make sure I've got the mechanics of this right. Inside the human body, potassium does not exist as that pure silvery metal Davy isolated. It exists as an ion.
Yes.
Meaning, when potassium is part of a compound, like the salts in our food, it has already reacted. It has already given away that unstable 19th electron.
Precisely. It has already gone through its chemical fire, so to speak. Once it gives away that electron, it becomes a stable particle. But because it lost a negatively charged electron, the potassium particle now carries a positive electrical charge. We call that an ion.
So it's safe in water now, but it carries this tiny electrical voltage. It's essentially a deactivated bomb that has been repurposed into a microscopic battery.
And that electrical charge is exactly why it is so crucial for our survival. An adult human contains about 140 grams of potassium.
That's like the weight of a baseball just swimming around inside us.
It is, and almost all of it is safely stored inside your cells. These dissolved charged potassium ions act as your body's biological electrical wiring.
Wait, if it's a charged electrical particle floating inside my cells, how does that electricity actually do anything? Does it just sit there holding a charge?
Not at all. It moves.
Yes.
And its movement is everything. The cells in your body, particularly your nerve and muscle cells, have specialized gates in their outer membranes. They constantly pump sodium ions out of the cell and pump potassium ions into the cell. This creates an electrical imbalance, a gradient. The inside of the cell becomes negatively charged compared to the outside.
So it's literally building up a static charge, like pulling back the string on a bow.
Exactly. The cell is now primed. When your brain sends a signal to move a muscle, those gates suddenly fly open.
Oh, wow.
The potassium ions rush out, and the sodium ions rush in. That sudden swap of charged particles generates a tiny electrical spark. We call it an action potential.
And that spark travels down the nerve. That is amazing. So, for you listening to us right now, these potassium ions rushing in and out of your cellular gates are the only reason your nervous system can transmit the message from your brain to your foot to tap along.
Yeah, precisely.
It's the reason your muscles can physically contract so you can walk or blink or breathe.
And most critically, it's the reason your heart maintains a normal, steady rhythm. Your heart has specialized pacemaker cells. The rhythmic, automatic pumping of your heart is entirely governed by these electrical impulses. Potassium ions are the tiny conductors, making sure that the spark fires correctly, resetting the cellular battery beat after beat after beat.
But if our bodies are constantly relying on this delicate electrical swap, the margins for error have to be incredibly small. If that balance gets thrown off, the whole biological battery fails, right?
It does. The human body goes to extraordinary lengths to regulate ionic potassium levels in the blood. If those levels fall out of regulation, like if they get too high, a condition called hyperkalemia, or too low, hypokalemia, the electrical system starts to misfire.
I was looking at the clinical data on this, and the physical symptoms of an imbalance are terrifying.
They really are.
Because if the cellular battery can't build up a charge, the nerves just stop working. You get severe muscle weakness where your limbs simply don't get the signal to move properly.
And the most immediate danger is to the heart. Without the precise concentration of potassium ions to govern the electrical reset after every beat, you develop abnormal heart rhythms, or arrhythmias.
Oh, geez.
If the imbalance becomes severe enough, the electrical signals fail completely, leading to cardiac arrest. Your life quite literally depends on maintaining the exact right amount of this element inside your cells.
So if we are constantly using these ions and losing them through sweat and normal kidney function, it means we have to constantly recharge the battery. We have to consume it.
Ah, yes.
Now, I know immediately everyone listening is picturing a banana. Bananas have somehow hired the best PR team in the fruit kingdom when it comes to potassium.
They really do have great PR. But we have to bust the banana myth here. Bananas are a good source, providing about 400 milligrams each, but they are far from the richest source of potassium available to us.
Yeah, if you really want to up your potassium intake, there are much heavier hitters out there. Nutrient-dense alternatives like baked potatoes and sweet potatoes are fantastic. Spinach and other leafy greens are huge.
Yeah, dark greens are great.
Right. And then you've got avocados, beans, coconut water, plain yogurt, wild-caught salmon, tomatoes, and dried fruits like apricots.
It's a very diverse list of foods. The daily recommended intake for adults is quite high, around 3,400 to 4,700 milligrams, depending on the specific guidelines, because we use so much of it.
That is a lot.
It is. The good news is that a normal, diverse diet provides all the potassium a healthy person needs. Your kidneys are masterful at filtering out any excess, so you don't usually need to overthink it unless a medical professional tells you to.
But looking at that list of foods, potatoes, spinach, beans, avocados, it brings up another point. We need potassium, but clearly the plants need it just as much if they're storing so much of it in their tissues. Why is a potato hoarding potassium?
Well, if we connect this to the bigger picture, plants rely on potassium just as heavily as humans do, but for a slightly different mechanical reason. Plants don't have nervous systems, obviously, but they do have to move water around.
Wait, how does potassium move water?
Through osmosis.
Oh,
Plants pump potassium ions into specialized guard cells that surround the pores on their leaves, which are called stomata. When the potassium rushes in, water follows it to balance the concentration. This swells the cells, opening the pores so the plant can breathe in carbon dioxide.
oh, that makes sense.
Yeah, and when it needs to close the pores to save water, it pumps the potassium out.
So without potassium, a plant can't regulate its water pressure, it can't breathe, and it can't grow.
Exactly. Because of this, agriculture on a global scale relies entirely on it. Potassium is one of the 3 primary nutrients in commercial fertilizers, usually in the form of potassium chloride or potash. We are mining this element in massive industrial quantities just to keep the world's crops growing and the food supply chain intact.
It's strange to think that the chemical Davy, isolated with a battery in 1807, is now being mined by the millions of tons. And human industry didn't just stop at farming. We took Davy's chemistry and ran with it.
It did.
Like, potassium hydroxide is widely used today in manufacturing liquid soaps and even modern alkaline batteries.
And we can't forget potassium nitrate.
Right. Historically, potassium nitrate, which is also known as saltpeter, has been a foundational ingredient in gunpowder, fireworks, and solid rocket propellants.
Yeah.
So even though nature found a way to use it safely as the spark for a human heartbeat, human industry still found a way to use its volatile nature to make things explode. It just can't escape that Jekyll and Hyde reputation.
It really can't. It is deeply ingrained in both human history and our biology. But if we zoom out even further, beyond the farms, the factories, and our own nervous systems, we see that potassium is not just a biological fluke. It is a foundational building block of the planet itself. It's the seventh most abundant element in the Earth's crust.
Seventh. That means we are constantly walking over massive planetary scale deposits of it.
We are. It exists naturally all around us.
Right.
Now, because it's so reactive, it's never in that pure metallic form. It's safely locked away as ions and common silicate minerals like feldspar and mica, which make up granite. It's part of the very bedrock we build our cities on.
And its reach doesn't even stop at the Earth's atmosphere. Astronomers have actually detected potassium inside our sun.
Yes, through spectroscopy.
How does that work again?
Well, when scientists analyze the like signatures coming from stars, every chemical element leaves a unique barcode, basically a specific wavelength of light.
Like a fingerprint.
Exactly. Scientists have found the unmistakable fingerprint of potassium, not just in our sun, but in distant stars light years away across the galaxy. It proves that this element was forged in stellar processes and distributed throughout the entire universe.
So what does this all mean? We've gone from a deadly...
In its pure metallic state, desperately trying to shed that single electron element 19, is one of the most reactive, dangerous, and explosive metals in existence. It requires absolute isolation under oil just to keep it from destroying itself and everything around it. But when nature strips away that extra electron and uses it in the right ionic form, it becomes quiet, invisible, and utterly essential. Without the electrical charge of potassium ions, plants could not breathe, muscles could not contract, nerves could not transmit a single thought, the human heart could not beat. It is the perfect chemical paradox.
The perfect chemical paradox. It really leaves you with a profound sense of awe about the atomic mechanics happening inside us every single second.
It's a fragile electrical balance, but an incredibly resilient one that connects the biology of our bodies directly to the elements forged in stars.
I want to leave you with a final thought to mull over today. The next time you sit quietly and feel your own pulse, maybe pressing 2 fingers to your wrist, I want you to think about what's actually happening under your skin.
It's pretty wild to think about.
Think about the fact that a substance that creates explosive, violent purple flames when it touches water in a laboratory is the exact same substance providing the microscopic electrical spark that is keeping you alive right now. It really makes you wonder what other supposedly dangerous elements are out there secretly working in your favor, keeping the whole biological machine running.
The periodic table is full of those kinds of beautiful contradictions.
It really is, and we are just getting started on this journey through it. Next, we'll discover element 20 calcium, the element that built your bones and changed the history of life. Until then, keep digging, keep questioning, and we'll catch you on the next deep dive.